So previously we talked about the isoparametric problem, which was optimizing a functional subject to constraints that took on the form of an integral that was equal to a constant. What we want to do in this section is talk about different types of equation constraints that we might put on the functional. So here we're going to derive the system of equations that must be satisfied by the set of functions. That set of function looks like, we'll call those u sub k for k different functions. There'll be functions of x, and these will be the functions that extremize the integral I, which will be some functional of u of k, integral from a to b of an integrand that looks like f, which is a function of x, u1 up through un, and then we're going to do u1 prime up through un prime. Okay, dx. We'll call this equation 1. This functional is going to be subject to, and we'll just go ahead and say that for the sake of this this discussion, that all the functions are defined at the boundaries. So uk, all the uk is evaluated at a, is going to be equal to some value called ak, and all the functions uk evaluated at b will be equal to some other corresponding values bk, where for k is going to be equal anything from 1 up to n. Okay, so that's the functional, and we're going to require that functional satisfy p independent constraint equations. And those equations are going to take the form, we'll say G, and there'll be a constraint equation R, which will be functions of x, u1 up through un, and u1 prime up through un prime equals 0. Right there, that's how our constraint equations are going to be formed. And R in this case goes from 1 up to p. Let's call this equation 2. Okay, it should be pretty obvious, but the requirement for these constraint equations is that the number of constraint equations has to be less than the number of functions involved. So in this case, where p is going to be less than n, we require that. Okay, let me give you a definition. Okay, if the equation constraint gr of x and whatever uk and uk primes there are equals 0, right? If that constraint equation is actually independent of the derivatives, okay, if that's the case, then we say that the equation, which now will look like gr of x and then uk, so there's no derivative terms, equals 0, that is referred to as a finite equation. Okay, so that obviously the general case in equation 2 could be a differential equation constraint. If there's no derivatives in there, then we refer to that constraint as a finite equation. Okay, so now we want to talk about how do we extremize the functional subject to these p-independent constraint equations. So what we're going to do is to extremize I of u of k, we're going to introduce n one-parameter families of varied functions. And these functions will be of the form where we would say u tilde of k, right? Remember u tilde being the varied path. Function of x is going to be equal to uk of x. Remember, this is the correct solution, the solution that extremizes the functional, plus epsilon times eta k. This is a variation, right? Eta k is a variation function of x. In this case, k is going to be going from 1 up to n. Okay, let's call this equation 3. Okay, because we've defined the functions on the boundaries, then we can say that the variation of the functions eta k evaluated at a and eta k evaluated at b in this case are equal to 0. We're also going to make the varied functions also have to satisfy the p constraints. So what that means is that we would say then that all of the g r constraints, which will be functions of x, now are must be true for the varied paths as well. So we'll call that u tilde k and then u tilde k prime equals 0. And that's for r equals 1 up to p. Okay, let's call this equation 4. So this proceeds exactly like we've done when we developed the Lagrange multiplier approach for extremizing functionals. What we've basically done in doing this is now we've created a varied functional that's really just a function now of epsilon. Okay, so we would write that, and we'll write this varied functional here as now I of epsilon will now be equal to the integral from a to b of f x u1 tilde up to un tilde and then u1 prime tilde up to un prime tilde. Right? Remembering that all the u tilde values are functions of epsilon, right? Well, epsilon and x, right? X being integrated out, so we're left with just simply a function of epsilon. Let's call this equation 5. Okay, so we know how to extremize a function, right? We take the derivative with respect to the variable and set it equal to 0. So that's what we're going to do next. So now we require that di of epsilon with respect to epsilon is equal to 0. Call that equation 6. Okay, one other thing I want to point out, remember when we had done this in the past, when we convert this to a function of epsilon, it's an extreme value. We can remove the tilde, right, when epsilon equals 0. So we're going to evaluate this derivative at epsilon equals 0. Okay? When we do that, this leads directly to the following. So taking that derivative of equation 5 and setting it equal to 0 and taking epsilon equal to 0 gives me integral from a to b of the quantity partial of f with respect to u1 times a to 1 of x, right? Why u1 instead of u1 tilde? It's because we took it at epsilon equals 0, which is where u1 tilde equals u1, okay? Then we go plus dot 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 all the way up to partial of f with respect to un times a to n of x plus the partial of f with respect to u1 prime a to 1 prime of x plus dot 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 plus the partial of f with respect to u n prime a to n prime of x, close brackets, dx equals 0. Let's call that equation 7. Now you may have been wondering, you'd be saying, well, I'm using a single epsilon, but I have all these different eta values, and I still have to satisfy these constraints. So are all these eta functions, are they all independent? And the answer is no, they're not. So we can't proceed in our typical fashion from equation 7, right? Because of the mutual dependence of the functions of eta. Or we'll say all the functions eta k, right? Functions of x. Okay, so to obtain the explicit expression of this dependence, we're going to note that each of the p equations in equation 4 must be satisfied for all epsilon. Okay? We're going to go ahead now and we can differentiate equation 4 with respect to epsilon to get the following. We end up with the partial of GR with respect to U1 tilde, right? We haven't yet set that we're evaluating this at epsilon equals 0, times a to 1, I've dropped the of x just for compactness, plus plus partial of GR with respect to UN tilde of a to n plus the partial of GR with respect to U1 prime times a to 1 prime plus plus partial of GR with respect to, oops, and I forgot my tilde there, UN tilde prime a to n prime. And that's all going to be equal to 0 for r goes from 1 to p, right? Call this equation 8. So now if we go in and say for epsilon equals 0, we remove our tildes and we write as follows. So we have partial GR with respect to U1, a to 1, plus plus partial of GR with respect to UN, a to n, plus partial of GR with respect to U1 prime, a to 1 prime, plus plus the partial of GR with respect to UN prime, a to n prime equals 0. We'll call that equation 9. Again, from r goes from 1 to p. So somehow we need to figure out a way to account for the mutual dependence of the eta functions. What I'm going to do next isn't obvious, but hopefully it'll become clear in retrospect. But we're going to multiply each equation represented by equation 9 by some arbitrary function. And we call that function, we're going to call it lambda of r. R corresponds to the particular GR we're looking at. And it'll be a function of x. And it's going to be called a Lagrange multiplier function. Okay? And then we're going to add all the resulting equations to get the following. So we end up with something like the sum from r equals 1 to p of the function lambda r of x times what we have in equation 9, right? For each, there's all these p equations represented. So we have partial GR with respect to U1 times a to 1 plus plus partial of GR with respect to UN times a to n plus partial of GR with respect to U1 prime times a to 1 prime plus plus the partial of GR with respect to UN prime times a to n prime, right? And since all of those collectively equals 0, the sum of those also collectively equals 0. So that equals 0, and we call that equation 10. Now what I'm going to do is I'm going to integrate equation 10 from a to b, and I'm going to add the result to equation 7 to get the following. So I end up with the integral now from a to b of, and I'll put a brace here, that first part of, I'm going to shorthand this a little bit. This is coming from equation 7 now. This is the partial of f with respect to u1 times a to 1 plus all the way up to the partial of f with respect to un prime times a to n prime, right? You can go up, and that's a little bit more compactly than I've been writing it before, but this is getting to be kind of a long integrand. So then I'm going to add to that the integrated version of equation 10, which is the sum from r equals 1 to p of lambda r of x times, again, I'm going to shorthand this and say partial of gr with respect to u1 plus ... all the way up to the partial of gr with respect to un prime. Whoops, and I forgot my etas here. This should be eta 1. And then this becomes eta n prime. Okay, and I'll close my bracket there, and then I'll close my brace. And I'll say this is dx equals 0. Call that equation 11. What I want to observe is that equation 11 is the first variation of an auxiliary functional that we'll call I star, okay, where I star looks as follows. Looks like the integral from a to b of some integrand f star, which is a function of x, uk, and uk prime dx. Let's call that equation 12. Okay, and let me also define what is f star in this case. Well, f star, so I'll just say, and f star of x, uk prime is equal to the integrand from the original functional, which is just f of x and uk prime. Again, using some shorthand there. And then that's going to be plus the summation from r equals 1 to p of lambda r of x times gr of x, u, k, and uk prime. Okay? These will collectively be called equations 12. Okay, so that's what we're observing. So really, equation 11 looks like extremizing the auxiliary functional I star, and we set it equal to 0 clearly. And so what would we typically do with equation 11? Well, we would see all of the derivative terms and the eta primes, and so we'd integrate by parts, and so that's what we're going to do next. Okay, so integrating 11 by parts. All right, we end up with the integral now from a to b. Here's my brace. And then inside here, this term becomes the partial of f star with respect to u1 minus d by dx partial of f star with respect to u1 prime. Okay, that term multiplied times eta 1 of x plus, and we do this for all of the eta n terms, and we end up with this the summation here. Now this is partial f star, partial un now, minus d by dx of partial f star with respect to un prime, close brackets, times eta n of x. We'll go ahead and close the brace here. Dx equals 0, and we'll call that equation 13. Okay. What I want to do again is I want to remind you that the eta k x functions are not independent. Okay, so why? Because they're related by the p constraint equations. Okay, so as a result, we really have n minus p independent eta k's. Okay, so since these are all arbitrary and I'm free to choose them, I can say that without loss of generality, I'm going to suppose that the first 1 through p eta functions are the functions that depend on the arbitrary functions eta p plus 1 to n, right? So I'm going to say that I'm going to arbitrarily define which of my etas are dependent, okay? So without loss of generality, we're going to suppose that, let's say, eta 1 up through eta p, right? So that's the same number of eta functions as I have constraint equations. So those are going to be functions that depend on the arbitrary functions eta p plus 1 up through eta n. Okay, so eta p plus 1 up through eta n are truly arbitrary, right? Such that we could, if they were in equation 13, we could break those out, apply the fundamental lemma of variational calculus to get the Euler-Lagrange equations that stem from that. Okay? So now we're going to come back to those Lagrange multiplier functions that I introduced earlier. We're going to assign those unspecified functions lambda r to be any set of functions that make the coefficient terms on eta 1 through eta p vanish. Okay? So what does that mean? If you go back and look at equation 11, there's a lambda term inside of f star, right? And what we're saying is that those lambda terms are going to take on a value such that this term in square brackets is 0, right? We're going to force lambda to take on such a value, the lambda to take on such a value that happens for all terms eta 1 through eta p. So what does that mean? That means thus we could write that those coefficient terms, which is what I'm writing here, the partial of f star with respect to uk minus d by dx of partial of f star with respect to uk prime equals 0, right? That's what we're meaning. This is a coefficient term on the eta term, right? Okay, and this is going to be true for k equals 1 up to p. Okay, you'll note that we got to this without invoking the fundamental lemma, right? What we did is we placed a special requirement on the Lagrange multiplier function. Okay, so what that means is that all of those terms vanish in equation 13 because of the choice that we made on lambda r of x for each of those p lambda values, or lambda functions rather. So in equation 13, we're left with the following. Okay, and it's just going to be only the p plus 1 and beyond terms. So now this becomes integral from a to b. Here's my brace. There's the first term here. This is now partial of f star with respect to u. Now this goes as the p plus 1 term minus d by dx of partial of f star with respect to u prime. This is the p plus 1 term of u. Okay, close brackets. That's multiplied times the eta. This is the p plus 1 eta of x. Remember, this is now arbitrary. It's not dependent because we removed all the dependent ones. Okay, and then we'll add that all the way up to the nth term. This is partial of f star with respect to now un minus d by dx. Partial of f star with respect to un prime. Okay, and this is going to be multiplied times eta n prime. Eta n rather. Okay, and close my brace. And that's going to be dx equals 0. Let's call this equation 15, right? So now 15 is in a form, because all my etas are arbitrary that are remaining, now I can invoke the fundamental lemma, right? The fundamental lemma of variational calculus, right? Because the remaining eta k's are arbitrary, okay? And the end result is n Euler-Lagrange equations of the form, looks like partial of f star with respect to uk minus d by dx, partial of f star with respect to uk prime equals 0 for k equals 1 to n. Let's call this equation 16. So how did we get that? Well, we got that equation is exactly the same as equation 14. So for the first p equations, those come from how we've chosen to define our Lagrange multiplier functions. And for the p plus 1 to n terms, those same equations come from invoking the fundamental lemma of variational calc. Okay? So what we have, though, is now we have n plus p unknown functions. And those unknown functions are, we have all of our uk of x, right? And well, that's going to go from k equals 1 up to n. So there's n functions that are unknown. We also have all of our lambda r functions that we don't know, right? And that goes from r equals 1 up to p, right? Equation 16 only gives me n equations to solve for n plus p functions. Okay, but we actually do now have n plus p functions, right? So let me show you. So we have n plus p functions, equations rather, to solve for these functions. Okay, so that first one is equation 16, right? So that's just partial of f star with respect to uk minus d by dx, right? Partial of f star with respect to uk prime equals 0 for k equals 1 to n, right? That's our n. But we also have all of our constraint equations, right? Which is that gr of x u1 up through un and u1 prime up through un prime, right? We have r, those go from r equals 1 up to p, right? So we have n plus p equations to solve for these n plus p functions. So that's the overall, that's how we go about solving this class of problems. It'll be a little bit more clear a little later on when I do an example of geodesics, where we're trying to use let's say the equation of a sphere, and we want to talk about how paths on that sphere can be extremized. And so look forward for that coming up.